Welcome back, or welcome for the very first time, to The Science Pillow, the channel where the universe is your lullaby, where facts are your blanket, and where the quiet hum of scientific curiosity gently guides you toward rest. If you're new here, this is a place designed for you. We make long-form educational content for curious minds who want something richer than silence, something more nourishing than noise, and something far more interesting than staring at the ceiling. If that sounds like you, then settle in, because tonight we are going somewhere extraordinary. Not out into space this time, but inward, into the very planet beneath your feet. Before we begin, if you haven't already, please consider hitting the subscribe button and giving this video a like. It genuinely helps the channel grow. It helps more curious people find their way here, and it only takes a second. You can always do it at the end if you'd prefer to stay in the moment for now. And now, with that said, let yourself breathe out slowly. Let your body relax into whatever surface it's resting on, and allow the words to carry you gently into the extraordinary story that's unfolding right beneath where you stand. The calming sleep scenario. Imagine, for a moment, that it is a clear and quiet night in late autumn. You are lying in a wide, open field somewhere far from city lights, somewhere that still knows the meaning of true darkness. The grass beneath you is cool and slightly damp, but there is a blanket beneath you and a blanket over you, and you feel entirely held, warm at the core, pleasantly cool at the edges. The sky above is vast and deeply, impossibly dark, and it is scattered with more stars than you have ever seen in one place. The Milky Way, that great pale band of light, sweeps across the dome of the heavens from horizon to horizon. You can see it clearly tonight. It looks like spilled milk on black velvet. You can hear almost nothing, perhaps a distant owl, perhaps the barely audible sound of your own breathing, steady and slow. Now, here is what makes this moment interesting. As you lie there, looking upward, something shifts in your awareness. Instead of feeling like a small thing looking outward at something enormous, you begin to feel the other direction too. You become aware, somehow, of what is beneath you. Not just the grass, not just the soil, not just the rock, but all the way down, thousands of kilometers down, down through crust and mantle and liquid metal and more, all the way to the very center of the earth, where something extraordinary has been quietly happening and has only recently been discovered. The planet you are lying on is not still. The planet you are lying on is not silent. The planet you are lying on is not even the same planet it was 20 years ago, or 100 years ago, or 1,000. Something is shifting. Something is changing. And the scientists who study it are sitting up straight in their chairs, looking at the data with wide eyes and saying, very quietly but with complete sincerity, something really unusual is happening to Earth. Tonight, we are going to find out what that is. Section 1. Introduction: A Restless World. Let's begin with something that sounds almost absurdly simple and becomes more astonishing the more you sit with it. Everything you have ever known, every place you have ever been, every person you have ever met, every building that has ever been built, and every mountain that has ever been climbed. All of it exists on a thin shell, wrapped around a churning, boiling, seething, spinning, shifting mass of rock and metal and fire that extends more than 6,000 kilometers to the center of the earth. The shell you live on, the crust, is in most places between 5 and 70 kilometers thick. If the earth were the size of an apple, the crust would be thinner than the apple's skin. And yet, On this thin shell we have built cities, grown forests, dug up history, watched civilizations rise and fall, and developed the technology to peer, however dimly, into the interior beneath us. What is down there has always been the great mystery. Long before seismology, before plate tectonics, before any of the scientific frameworks we now take for granted, people sensed that the Earth was alive in some deep way. Volcanoes erupted. Earthquakes shook the ground without warning. Hot springs bubbled up from nowhere. The soil itself seemed to breathe in places, trembling and shifting under the feet of those who walked upon it. Ancient cultures told stories about this. Gods of fire and earth, underworlds of heat and struggle, a deep and restless power beneath the surface of ordinary life. They were not wrong in their instinct. They were simply missing the technical language to describe what they were feeling. That language came slowly. It came through geology and chemistry and physics, through centuries of careful observation, through the development of seismographs that could detect vibrations from earthquakes on the other side of the planet. It came through the shocking revelation, accepted only in the mid-20th century, after decades of resistance, that the continents themselves are moving, drifting across the face of the planet on enormous tectonic plates, colliding and separating, creating mountain ranges and ocean trenches and volcanic chains as they go. The discovery of plate tectonics was one of the most profound shifts in scientific thinking of the modern era. Before it, geologists looked at a world that seemed fundamentally static, punctuated by dramatic but local events. After it, they saw a world in constant, slow, planet-wide motion. But even that discovery, revolutionary as it was, described only the outermost layer of the Earth, the crust and the topmost mantle, the part that breaks and slides and drifts. Deeper than that, the story was much harder to read. The only way to read it, even today, is through seismology, the study of the waves that earthquakes send traveling through the Earth's body. When a large earthquake occurs, it sends seismic waves radiating outward in all directions, like ripples from a stone dropped into a pond. But unlike the ripples in a pond, which move only across the surface, earthquake waves dive deep into the earth, bending and reflecting and changing speed as they pass through layers of different density and composition. By monitoring these waves at stations around the globe, scientists can build a picture of what the Earth looks like inside, rather like a doctor using an ultrasound to see an organ that cannot be observed directly. And what they have been seeing in recent years, especially as the technology has grown more sensitive and the databases of seismic measurements have grown larger, has genuinely surprised them. Something is changing in the deep Earth. Several things, in fact. And while none of these changes are cause for panic, none of them are about to swallow cities or darken the sky, they are deeply fascinating, genuinely mysterious, and in some cases quietly consequential for the world we live in. Tonight, we are going to explore all of them, one by one, in the same calm and curious spirit in which the scientists themselves approach them. We are going to descend through the layers of our planet, through its crust and mantle and outer core and inner core, and we are going to see what we find. Let yourself breathe easily. There is nothing alarming in this story. Only wonder, only depth, only the extraordinary reminder that the ground beneath your feet is not the simple, solid, sleeping thing you have always assumed it to be. Section 2. The Heart That Changed Direction, Earth's Inner Core. Let us begin at the very deepest place we can reach, the inner core. To understand the inner core, we first need to understand the structure of the Earth from the inside out. At the very center, extending from the Earth's absolute center to about 1,221 kilometers out, is the inner core. It is a solid ball of mostly iron and nickel, and it is extraordinarily hot, somewhere between 5,000 and 7,000 degrees Celsius, roughly comparable to the surface temperature of the Sun. The pressure at the center of the Earth is about 360 gigapascals, or 3.5 million times the air pressure at sea level. Under those conditions, iron behaves differently than we might expect. Despite the intense heat, the enormous pressure keeps the inner core in a solid state, though recent research in 2025 suggested it may actually be in a superionic state, where carbon atoms flow freely through a solid iron lattice, making it a kind of strange hybrid between solid and liquid. Surrounding the inner core is the outer core, a layer extending from about 1,221 kilometers to 3,480 kilometers from Earth's center. Unlike the inner core, the outer core is liquid, a vast ocean of molten iron and nickel, swirling and churning in complex patterns driven by heat rising from the center and by the rotation of the Earth itself. This movement of electrically conductive liquid metal is what generates Earth's magnetic field through a process called the geodynamo. The outer core is, in a very real sense, a natural electrical generator, and the magnetic field it produces is one of the most important things about our planet, because it shields us and all life on Earth from the constant bombardment of charged particles and radiation coming from the Sun. Beyond the outer core is the mantle, a vast region of hot, solid, but slowly flowing rock extending from about 3,480 kilometers depth all the way to roughly 35 kilometers below the surface, and above that is the thin crust, the skin of the world that we walk upon. Now, back to the inner core. For decades, scientists who studied the inner core had a broad understanding of it. It was solid, it was hot, it was mostly iron, and it appeared to rotate slightly faster than the rest of the Earth. This superrotation of the inner core, as scientists called it, was proposed in the mid-1990s and seemed for a while to be a fairly settled piece of science. The inner core spun a little faster than the planet itself, perpetually lapping the surface in a slow geological waltz. That picture began to change. And the change accelerated dramatically with research published in 2023, and then confirmed with greater precision in a landmark paper published in the journal Nature in June 2024. Here is what scientists found when they compiled and analyzed 143 pairs of matching earthquakes recorded over the period from 1991 to 2023, all originating in the same region, the South Sandwich Islands in the Atlantic Ocean, and all sending their seismic waves along similar paths through the Earth's interior. The team, led by seismologist John Vidal and his colleague Wei Wang, had a brilliant method. They looked for pairs of earthquakes that were essentially identical. The same location, the same depth, the same magnitude, sending virtually identical waves through the Earth. These are called repeating earthquakes, or doublets. Because the earthquakes were so similar to one another, any differences in the seismic waves they produced at distant recording stations could only be explained by changes in the medium those waves traveled through. In other words, changes in the Earth's interior. What they found was this. The inner core had been spinning faster than Earth's surface from at least the 1990s through about 2003. Then, gradually, it began to slow. By 2008, it had slowed to a point where it was essentially spinning at the same rate as the rest of the planet. And then something remarkable happened. After 2008, the inner core continued to slow, until it was actually rotating slightly slower than the planet's surface. In other words, it had reversed its relative spin direction. The inner core was now, in the most precise technical sense of the word, backtracking, moving backward along its earlier path relative to the surface of the Earth and the overlying layers. This is not science fiction. It is not a conspiracy. It is a finding published in Nature, one of the world's most prestigious scientific journals, confirmed by multiple independent teams using different data sets. The inner core of our planet has changed its relative direction of rotation within the span of recorded scientific history. Now, the very first thing to understand is that this change is extremely subtle. The inner core is not dramatically spinning backward like some doomsday scenario in a disaster film. The speeds involved are tiny fractions of a degree per year, amounts so small that they can only be detected with the most exquisitely sensitive seismic instruments and decades of patient data collection. The practical consequences for life on Earth's surface are essentially undetectable on human timescales. The length of the day may be affected by a tiny fraction of a millisecond, far too small for any person to notice. But for scientists, the implications are profound, because this raises an immediate and fascinating question. Why? Vidal's team proposed that the inner core's change in rotation is driven by the ongoing tug-of-war between two enormous forces. On one side, Earth's magnetic field, generated by the churning liquid outer core, exerts a pull on the solid inner core, dragging it in one direction. On the other side, the gravitational attraction of the dense regions of the overlying mantle pulls in another direction. These two forces battle each other continuously, and the balance between them shifts over time, causing the inner core's rotation to oscillate in a pattern that may repeat on a cycle of roughly 70 years. If this is correct, the last time the inner core underwent a similar reversal would have been around the 1970s, and the next time would be sometime around 2040 or 2050. But the discoveries did not stop at rotation. In February 2025, the same research team published a follow-up study in the journal Nature Geoscience, and this one revealed something even more unexpected. The inner core is also changing shape. As the inner core spins and slows, it is not remaining perfectly spherical. Its surface, the boundary between the solid inner core and the liquid outer core surrounding it, is deforming. The liquid outer core appears to be pushing against the inner core in ways that create topographic features on its surface, structures that the researchers compared, almost poetically, to landslides. The outermost layers of the inner core are being reshaped over time, pushed and pulled by the churning liquid that surrounds them. Think about what that means for a moment. The innermost solid region of our planet, a sphere of iron under pressures 3.5 million times greater than our own atmosphere, sitting at temperatures close to the surface of the sun, is morphing. It is not static. It is not eternal and unchanging. It is alive in its own geological way, shaped by forces we are only beginning to measure. What does all of this mean for life on the surface? Scientists are cautious about drawing direct lines between changes in the deep interior and events at the surface. The inner core's rotation does influence the magnetic field, which does protect us from solar radiation, which does affect everything from animal migration to satellite communications to the aurora borealis dancing across polar skies. But these are slow processes, playing out over decades and centuries. There is no alarm to raise. There is only the quiet, exhilarating awareness that the planet's deepest engine is far more dynamic, far more restless, and far more surprising than anyone imagined even a generation ago. As the scientists studying this put it, the inner core is not a steady metronome. It is a restless sphere, tied by forces we are only beginning to quantify. And the story of what is happening down there is still being written, one earthquake at a time. Section 3. The compass that won't sit still. Earth's wandering magnetic field. Let's move outward now, from the solid inner core to the liquid outer core, and trace the force that the churning of that liquid ocean of molten metal produces. The magnetic field that wraps our entire planet in an invisible protective sphere. You have probably used a compass at some point in your life. You hold it level in your hand, and the needle swings to point at magnetic north. What you may not have thought much about is that magnetic north and geographic north are not the same thing. Geographic north is the fixed point at the top of the Earth's rotational axis, the place where all lines of longitude converge in the northern hemisphere. Magnetic north is something different entirely. It is the place on the surface of the Earth where the planet's magnetic field lines point vertically downward, and it is defined by the behavior of the molten iron in the outer core far beneath. And unlike geographic north, which has been fixed for all of recorded human history, magnetic north moves, constantly. This was understood long before we knew why it happened. Early navigators noticed that their compass readings drifted over time if they returned to the same location. The problem was significant enough that in areas where precise navigation was critical, harbors, airports, shipping lanes, the official designations had to be periodically updated to account for the shifting field. But the rate of movement was slow enough that it could be accommodated without great difficulty. Then something changed. Around 1990, the magnetic North Pole, which had been drifting slowly southward and westward in Canada's Arctic for most of recorded history, accelerated dramatically. Over the following decades, it picked up speed to a degree that genuinely alarmed scientists. In the 1990s and early 2000s, it was racing northward at roughly 50 to 60 kilometers per year, a pace almost twice as fast as anything previously measured. It was moving so quickly that the World Magnetic Model, the official international standard used to set navigational readings for aircraft, ships, submarines, smartphones, and military systems, needed to be updated ahead of its regular 5-year schedule. An emergency update was released in 2019, 2 years early, because the models were diverging from reality faster than expected. Since its discovery by British explorer James Clark Ross in 1831 on Canada's Boothia Peninsula, magnetic north had wandered more than 2,250 kilometers. It had left Canada entirely and was heading toward Siberia with what seemed like determination. Researchers attributed the acceleration to changes in the flow patterns of molten iron in the outer core, specifically to the behavior of a pair of large-scale circulation patterns, or lobes of magnetic flux, one beneath Canada and one beneath Siberia. The Canadian lobe had been weakening while the Siberian lobe had been strengthening, and this imbalance was dragging the magnetic North Pole eastward at unprecedented speed. And then, almost as strangely as it had accelerated, the movement began to slow. By the mid-2000s, the pace had already dropped from its peak. By the time the latest World Magnetic Model, called WMM 2025, released in December 2024, was published, the pole's movement had dropped to about 45 kilometers per year, significantly slower than the sprint of the early 2000s, but still far faster than the gentle drift of previous centuries. Arnaud Chouliat, a senior research scientist at the University of Colorado Boulder and the NOAA National Centers for Environmental Information, noted that the forecast included in the 2020 model had proved remarkably accurate. The pole arrived roughly where scientists had predicted. But the underlying behavior, the dramatic acceleration followed by the apparent slowdown, remains unexplained. Scientists understand the broad physics. The poles wander because the flow of liquid metal in the outer core changes over time, and those changes alter the distribution of magnetic field lines on Earth's surface. But the specific mechanisms that triggered the 20th century acceleration and the forces that are now moderating it are still an active area of research. The World Magnetic Model 2025 also introduced something new for the first time, a high-resolution companion version called WMM-HR 2025, which offers much finer spatial resolution than previous models, approximately 300 kilometers at the equator, compared to the standard 3,300 kilometers. Think of it as the difference between a blurry satellite photograph and a crisp, detailed aerial image. This improved resolution means that navigational systems can be calibrated more precisely than ever before, which matters enormously for any application that depends on accurate heading information. Airlines flying over the polar regions, submarines navigating under Arctic ice, drilling equipment boring into the Earth at precise angles, and, of course, the compass inside your smartphone that you use to orient a map. The magnetic field affects more than navigation. It influences the behavior of every animal species that uses magnetism to navigate, which includes sea turtles, migratory birds of dozens of species, whales, dolphins, salmon returning to their birth rivers, and many others. These animals carry within their bodies what amounts to a biological compass, sensory systems that can detect the subtle variations in the Earth's magnetic field and use them to chart paths across ocean and sky. As the field changes, as magnetic north drifts, as the overall intensity of the field shifts in various regions, these animals must adapt or suffer the consequences. There is also evidence that changes in the magnetic field have effects on the upper atmosphere and on the amount of cosmic radiation that reaches the Earth's surface in different regions. The magnetic field acts like a giant force field, deflecting the constant stream of charged particles, protons, and electrons that the Sun constantly emits. In regions where the field is weaker, more of these particles can penetrate deeper into the atmosphere, potentially influencing cloud formation, chemistry, and other atmospheric processes. This is an active area of scientific debate, and the connections between magnetic field changes and surface phenomena are not fully understood, but they are being studied. In late 2023 and running into 2024, scientists detected what they call a geomagnetic jerk, a sudden rapid change in the rate of acceleration of the magnetic field. Jerks, which sound informal but are a real technical term in geomagnetism, represent significant rapid changes in the field's behavior. They happen on timescales of months to a couple of years, and are thought to originate in the outer core, potentially related to waves of magnetic instability that propagate through the liquid metal. The 2023 to 2024 jerk was noted in the 2025 State of the Geomagnetic Field Report published by NOAA, along with observations that the South Atlantic region of the magnetic field had continued to show unusual behavior and accelerated weakening. We are living, in other words, through a period of unusual magnetic activity, not catastrophic. Scientists are at pains to emphasize that we are not on the verge of a magnetic pole reversal, which would be a much longer and more complex process, but unusual, dynamic, worth paying attention to. And the most dramatic expression of that unusual activity is already visible from space. Section 4. The Hole in the Shield. The South Atlantic Anomaly. There is a region of the Earth's magnetic field, sitting over the South Atlantic Ocean roughly between South America and the southwestern coast of Africa, where the field is strikingly weaker than everywhere else. Scientists call it the South Atlantic Anomaly, and it has been known about for decades. But something has changed about it recently, and the change has been measured with an unprecedented level of detail by 3 satellites that have been circling the Earth since 2013. The European Space Agency's SWARM mission consists of 3 identical satellites, with a 4th added in 2018, each equipped with highly sensitive magnetometers that measure Earth's magnetic field from orbit. Since their launch in November 2013, they have been providing the longest, most detailed continuous record of magnetic field measurements ever made from space. And in October 2025, the scientists analyzing that data published a comprehensive study that revealed something striking. The South Atlantic Anomaly has grown by an area nearly half the size of continental Europe since 2014. Let that sink in for a moment. A weak spot in Earth's protective magnetic shield has expanded by approximately half the size of continental Europe in just 11 years. The minimum field strength within the anomaly fell from about 22,430 nanoteslas in 2014 to 22,094 nanoteslas in 2025, a drop of 336 nanoteslas. To put that in context, the average field strength at Earth's surface is around 25,000 to 65,000 nanoteslas depending on location, so the anomaly's field strength is already substantially below the global average, and it is continuing to weaken. What makes the South Atlantic Anomaly particularly interesting from a physical standpoint is what is happening beneath it. Normal magnetic field lines in most regions of Earth emerge from the Earth's core in the southern hemisphere and loop around through space to re-enter in the northern hemisphere. But beneath the South Atlantic Anomaly, something strange is going on. Some of the field lines, instead of emerging from the core as they should, are actually diving back into it. They are pointing the wrong way. As Chris Finlay, professor of geomagnetism at the Technical University of Denmark and the lead author of the SWARM study, explained in 2025, beneath the anomaly, there are unexpected areas where the field lines go back into the core rather than coming out of it, and this is contributing to the weakening. Something in the deep Earth is causing the magnetic field geometry to be fundamentally different in this region than elsewhere on the planet. Finlay's team also found that the anomaly is not simply growing uniformly. It is not a single, expanding blob of weakness. It is changing differently in different parts of its extent. The area near Africa has been weakening faster than the area near South America, especially since 2020. A region southwest of Africa, in particular, is showing unusually rapid field weakening, and the researchers suspect this is connected to patterns in the deep outer core. Meanwhile, in the northern hemisphere, changes have been happening that the scientists did not fully expect. The region of strong field over Canada has shrunk by an area roughly comparable to the size of India, while a separate strong field region over Siberia has grown by an area roughly comparable to the size of Greenland. Earth's magnetic field, viewed through the lens of these satellite measurements, looks less like a smooth, symmetric, slowly changing shield, and more like a living, turbulent system that is rearranging itself in real time, with some parts strengthening while others weaken, driven by the endlessly complex dynamics of the molten metal churning below. For practical human concerns, the most significant consequence of the South Atlantic anomaly's expansion is the increased hazard it poses to satellites and spacecraft. The magnetic field's job, from a space engineering perspective, is to deflect the energetic particles that the Sun constantly emits. Protons and electrons traveling at high speeds that can, if they hit sensitive electronics, flip bits in computer memory, corrupt data, damage sensors, or in severe cases cause permanent hardware failure. In regions where the field is strong, these particles are deflected before they reach satellite altitudes. But the South Atlantic anomaly is a region where the deflection is incomplete. Satellites passing over it are exposed to higher doses of radiation, and the effects are real and measurable. The Hubble Space Telescope, for example, routinely shuts down certain sensitive detectors when its orbit carries it over the South Atlantic anomaly, to protect them from radiation-induced malfunctions. The International Space Station, which orbits at an inclination that takes it through the anomaly regularly, has additional shielding to help protect its crew. A number of satellite failures over the years have been attributed, at least in part, to radiation exposure during passages over this region. Japan's Hitomi X-ray Observatory suffered a critical cascade of failures that ultimately destroyed the spacecraft, with the South Atlantic anomaly believed to have played a role in triggering the initial malfunction. As the anomaly expands, more satellites, carrying telecommunications, Earth observation, GPS, and other critical functions, will pass through larger volumes of elevated radiation on every orbit. The anomaly now covers roughly 0.9% of Earth's surface, and its continued growth means that the engineering challenges associated with it will increase. But here is the reassuring part, and it is important enough that we should pause on it clearly. The South Atlantic anomaly is not a sign that Earth's magnetic field is about to collapse or reverse. Scientists studying its history and the geological record have found that similar, regional weaknesses in the field have appeared and disappeared many times in Earth's past, without triggering pole reversals. What is more likely, according to the best evidence available, is that this is a medium-term fluctuation, playing out on timescales of decades to centuries, driven by the ever-shifting dynamics of the outer core. The field has weakened by roughly 10% over the last 2 centuries, but that rate of change, while significant, is within the range of natural variation seen in the longer-term record. A true pole reversal, where north and south swap places entirely, takes thousands of years to unfold, and shows specific patterns in the geological record that are not currently being observed. The message from the scientists is nuanced. If you are standing on the Earth's surface, the atmosphere provides so much additional shielding that the anomaly has no measurable effect on your daily life. The concern is for technology in orbit, not for people on the ground. And even for satellites, the anomaly is well understood enough that operators can plan around it, shutting down vulnerable systems during passes over the affected area, hardening future satellites against radiation damage, and tracking the anomaly's evolution carefully to stay ahead of it. What the South Atlantic anomaly most beautifully represents in the end is a window. It is a place where the deep Earth's activity, the complex, turbulent, magnetic dynamo of the outer core is expressing itself in a way that we can measure from space. It is a reminder that the forces shaping our planet are not confined to earthquakes and volcanoes and weather systems. They extend from the very center of the Earth to the edge of space, connected in ways we are still working to understand. Section 5. The Buried Continents, Hidden Worlds Beneath Our Feet. Let us go deeper again, and this time, let us travel to one of the strangest discoveries in recent Earth science. A discovery about things that have been hiding at the base of the mantle for 500 million years or more, only recently confirmed by a study published in the journal Nature in January 2025. The mantle of the Earth, as we noted earlier, is the vast region of hot rock that extends from the base of the crust down to the outer core, a depth range of roughly 35 to 2,900 kilometers. For a long time, scientists imagined the mantle as a relatively well-mixed system. Yes, it was hot. Yes, it was slowly flowing, more like thick putty than like rock as we usually think of it, moving on timescales of millions of years. But the general assumption was that this slow convection mixed the mantle fairly thoroughly over geological time, blending different materials together the way stirring a pot of thick soup eventually homogenizes the ingredients. That picture is being revised. And the revision started with the discovery, about 50 years ago, of two enormous anomalous structures sitting at the very bottom of the mantle, at the boundary between the mantle and the outer core. Seismologists first noticed them as anomalies in the way earthquake waves traveled through the Earth's deep interior. In certain regions at the base of the mantle, the waves slowed down significantly. Slowed so much that the regions they detected became known as Large Low Seismic Velocity Provinces, or LLSVPS. There are two of them, each roughly the size of a continent. One sits beneath Africa, the other sits beneath the Pacific Ocean. They are separated by roughly half the circumference of the Earth, positioned almost exactly on opposite sides of the planet. Between them, at the base of the mantle, lies a kind of graveyard. A vast accumulation of old, cold, sunken tectonic plates, the remains of ocean floors that have been swallowed back into the Earth over hundreds of millions of years at subduction zones around the globe. For 50 years, scientists have known about these two enormous structures, but what they could not determine was whether they were ancient or relatively recent features, whether they had been sitting at the base of the mantle for billions of years, or whether they were regularly reformed and reconstituted by the ongoing processes of mantle convection. This mattered enormously for understanding Earth's deep history, because if the LLSVPs are ancient, it means the mantle is far less well mixed than previously believed, and the deep interior of the Earth preserves a more complex, layered structure that stretches back to the very early history of the planet. The 2025 study from Utrecht University answered that question with a new technique. Arwen Daas, a seismologist and professor at Utrecht, and her colleague Sujanya Talavera Souza developed the first complete 3D model of mantle attenuation, the rate at which seismic waves lose energy as they travel through different parts of the mantle. This is subtly different from measuring wave speed. A wave can slow down for various reasons. The amount of energy it loses as it travels is a different kind of measurement, and it gives different information about the physical properties of the material it passes through. What they found was that the seismic waves lost relatively little energy when they passed through the LLSVPS, but they lost significantly more energy when they passed through the surrounding slab graveyard of sunken tectonic plates. This difference, it turns out, is diagnostic of grain size. In materials made of smaller mineral grains, seismic energy is dissipated at the many boundaries between grains. In materials made of larger grains, there are fewer boundaries, and energy loss is lower. And large mineral grains take a very long time to form. They grow at geological rates, accumulating mass over millions and tens of millions and hundreds of millions of years. The conclusion from the energy loss measurements was striking. The material inside the LLSVPs is made of much larger mineral grains than the surrounding slab graveyard material. This means the LLSVPs must be much, much older than the sunken plates around them, at least 500 million years old, possibly much older. These structures are not temporary features that form and dissolve and reform. They are ancient anchors, primordial provinces of the deep earth that have persisted through the assembly and breakup of supercontinents, through mass extinctions and evolutionary explosions, through everything that has happened at the surface in at least the last 500 million years. As Dius noted, nobody knew whether these structures were only a temporary phenomenon, or if they had been sitting there for millions, or perhaps even billions of years. Now we know they are ancient, and that changes everything about how we think about the deep earth. Because if the LLSVPs are ancient, then the mantle is not a well-stirred pot. It is a stratified, complex system where some structures persist essentially unchanged across geological epochs, while others, the sunken slabs, are constantly being added to and gradually modified. The mantle has memory. It preserves the history of the Earth's interior in ways that are only now beginning to be read. There is one more remarkable thing about the LLSVPs. They appear to be the source of mantle plumes, great upwellings of hot material that rise through the mantle from the base to the surface, feeding volcanic hotspots like Hawaii and Iceland. The volcanoes of the Hawaiian chain, for instance, sit above a hotspot that has been active for tens of millions of years, leaving a trail of progressively older islands stretching westward across the Pacific as the tectonic plate has moved over it. That hotspot is thought to originate from the edges of the Pacific, LLSVP, deep at the base of the mantle. In a very real sense, the lava that erupts in Hawaii today may carry material that has been sitting at the base of the mantle since before complex animal life existed on Earth's surface. The discovery of the LLSVP as great age does not change anything about everyday life on the surface, but it fundamentally deepens our understanding of what kind of planet we live on. We live on a planet whose interior is more layered, more complex, more ancient, and more historically rich than we imagined. We live on a planet that has preserved parts of its deep past in a kind of geological memory that only the most sophisticated seismic measurements are beginning to decode. 2 hidden continents buried deep within the Earth. We tend to think of the Earth's mantle, the vast zone of rock between the crust we walk on and the molten outer core beneath, as a place of slow, uniform flow. Convection currents of hot rock rising and cool rock sinking, like an extraordinarily slow version of water boiling in a pot. We imagine it well stirred, homogeneous, the billions of years of churning having blended everything together. This was the dominant model for a long time. It is wrong, or at least it is far more complicated than we thought. In the deepest part of the mantle, at the boundary between the rocky mantle and the fluid outer core, a boundary that sits about 2,900 kilometers below the surface, there are 2 structures that violate everything the simple model predicted. 2 vast regions of rock that are hotter than their surroundings, significantly different in composition from the rock around them, and, remarkably, rigid and stable in a zone where everything should theoretically be mixed and in motion. Scientists call them Large Low Seismic Velocity Provinces, or LLSVPs. The name describes what distinguishes them. Seismic waves passing through these regions travel more slowly than they do through the surrounding mantle, the way sound moves differently through different materials. Each of these regions is enormous. Together, they cover roughly 20% of the boundary between the mantle and the outer core. In some places, they tower nearly 965 kilometers tall. One lies beneath the African continent. The other lies beneath the Pacific Ocean. They have been known to exist since the late 1990s, when seismic data first revealed their presence. But for a long time, almost nothing was known about what they were made of, how old they were, or what role they played in the broader dynamics of the mantle. Were they remnants of ancient, subducted rock from the surface? Were they primordial material left over from the earliest formation of the Earth? Were they actively influencing the movement of tectonic plates above them? In January 2025, a study published in Nature by researchers from Utrecht University brought the clearest answers yet. Using a new analytical approach that examined not just how fast seismic waves moved through the LLSVPs, but also how much energy those waves lost as they passed through, a property called attenuation, the researchers found something unexpected. Seismic waves passing through the slab graveyards surrounding the LLSVPs, the regions filled with remnants of ancient tectonic plates that had been subducted into the mantle over hundreds of millions of years, lost a significant amount of energy, becoming quieter and more muffled. But the waves passing through the LLSVPs themselves retained their energy much better. They slowed down, but they did not dampen. Lead researcher Sujanya Talavera Souza and her colleagues traced this difference to grain size. In the surrounding slab graveyards, ancient tectonic plates had been compressed and reformed, creating rock with very small mineral grains. In the LLSVPs, the mineral grains were much larger, dramatically larger, suggesting that these structures had remained largely undisturbed for an extraordinarily long time. Large grains are a signature of age, of stability, of rock that has been allowed to sit and settle and slowly crystallize without being disrupted. The conclusion: these subterranean islands are ancient, at least 500 million years old, perhaps older still. Perhaps some researchers have speculated as old as the Earth itself, relics of the planet's earliest formation, somehow surviving while everything around them was stirred, subducted, and remixed over and over across geological time. There is less flow in Earth's mantle than is commonly thought, the Utrecht team wrote, overturning a piece of conventional wisdom that had guided mantle dynamics research for decades. The implications extend beyond pure geology. These two enormous buried continents may function as anchors in the mantle, stable reference points around which convection currents organize, fixed features in an otherwise mobile system. They may influence the locations of volcanic hotspots at the surface, the Hawaiian Islands, Iceland, the Azores, which are thought to form above upwelling plumes of hot material rising from the deep mantle. If the LLSVPs are indeed ancient anchors generating these plumes, then the pattern of volcanic hotspots on Earth's surface may have been partly determined billions of years ago, when these buried islands settled into their current positions and began doing whatever it is they do down there in the dark, at the boundary of rock and iron, at the edge of our understanding. And they are not alone down there. Surrounding them is that graveyard of ancient tectonic plates, slabs of oceanic floor that were once, on the surface, were pushed beneath continental edges by the restless drift of plate tectonics, and sank slowly through the mantle over millions of years. Some made it all the way to the core mantle boundary. Some got stuck partway down, hanging in the mantle transition zone, a region between about 460 kilometers depth where the pressure causes the minerals in rock to reorganize into denser structures, sometimes halting the descent of subducted slabs. In September 2024, researchers from the University of Maryland published a study in Science Advances describing the discovery of one of these stuck slabs beneath the East Pacific Rise. A piece of ancient seafloor that sank into the mantle roughly 250 million years ago, during the age of the earliest dinosaurs, and has been there ever since, barely moving. The seismic imaging showed material sinking through the mantle transition zone at roughly half the speed scientists would normally expect, suggesting this region of the mantle can act as a slow, viscous barrier, catching and holding pieces of ancient Earth in a kind of geological suspended animation. As Jingchuan Wang, the lead researcher on that study, described it, the mantle transition zone can act like a barrier, slowing the movement of material and holding it in place. Pieces of ancient ocean floor, some of them dating back to epochs when the first dinosaurs were learning to walk, sit frozen in the deep earth today, recorded by the ghost-like traces they leave in seismic data. Cold and quiet. Time capsules from the Triassic period, still descending in geological slow motion. The Earth is full of its own history. Every layer of it contains records, memories, evidence of what came before. We are just learning how to read them. Section 6. Continents peeling from below. A new kind of geological discovery. The most recent chapter of the story of Earth's hidden interior came in November 2025, in a study published in the journal Nature Geoscience by researchers from the University of Southampton, working with colleagues from institutions in Germany and Canada. For decades, one of the enduring puzzles in Earth science had been this: why do volcanic islands and seamounts located far out in the middle of ocean basins, far from any tectonic plate boundary, far from any known subduction zone, sometimes contain chemical signatures that look distinctly continental? When geologists analyze the rock from these mid-ocean volcanoes, they find isotopic ratios and trace element abundances that are normally associated with continental crust, not with the mantle material that should be producing oceanic volcanism. The rock from these islands has been contaminated, somehow, by continental material. But how does continental material end up in the middle of the deep oceanic mantle, thousands of kilometers from the nearest continent? The standard explanations that geologists had proposed over the years, that the contamination came from ocean sediments being dragged down into the mantle at subduction zones, or that it came from deep mantle plumes, worked in some cases but failed in others. Some of these volcanic regions showed too much continental signature to be explained by sediment recycling. Others seemed too shallow and cool to be driven by the deep mantle plumes that would be needed to bring material from such great depths. Thomas Gernon, professor of earth science at the University of Southampton, and his colleagues proposed a completely different explanation. Continents, they suggested, do not just split apart at the surface when tectonic forces pull them apart, they also peel away from below. And the peeling happens not just at the immediate edges where rifting is occurring, but far inward, stripping material from the continental roots, the deep bases of the thick, ancient lithosphere that underlies continental cores, and carrying it far into the oceanic mantle. The mechanism they described works like this. When tectonic forces begin pulling a continent apart, creating a rift and eventually a new ocean basin, the stress of that stretching creates waves of instability in the mantle. Slow-motion disturbances that Gernon's team called mantle waves. These waves propagate through the deep mantle at depths of 150 to 200 kilometers, rolling like invisible slow-motion tsunamis beneath the continental roots. As they pass, they destabilize the base of the continent, gradually stripping off fragments of the deep continental material and carrying them outward into the oceanic mantle. The process is slow, very slow on human timescales, but the evidence of its having happened is preserved in the chemical signatures of volcanic rocks that formed afterward. Gernon's team found compelling evidence for this process in the Indian Ocean. After the ancient supercontinent Gondwana began breaking apart more than 100 million years ago, a chain of volcanic structures in the Indian Ocean, known as the Indian Ocean Seamount Province, erupted with material that had an unmistakably continental chemical signature. But the signature faded over time, gradually becoming less pronounced over tens of millions of years, as the supply of continental material from below was slowly exhausted. This pattern matched precisely what the team's model predicted if continental material was being stripped from beneath the rifting continent and carried into the oceanic mantle, where it then slowly dispersed. Even more striking, the model predicted, and observations confirmed that this process continued for far longer and over far greater distances than anyone had previously thought. The mantle waves carrying continental fragments extended not just hundreds, but potentially thousands of kilometers from the original continental edge. The effects of a continental breakup that occurred 100 million years ago are still being felt today in the chemical signature of volcanoes that sit far out in the Indian Ocean, as though the mantle is still slowly digesting and redistributing the material that was stripped away when Gondwana fell apart. As Sascha Brune of GFZ Potsdam described it, the mantle is still feeling the effects of continental breakup long after the continents themselves have separated. The system does not switch off when a new ocean basin forms. It keeps moving, keeps reorganizing, keeps transporting material far from where it originated. This discovery adds yet another layer of complexity to our understanding of the deep Earth. The mantle is not passive. It is not simply the medium through which tectonic plates move. It is an active, dynamic system that takes in material from the surface, processes it over millions of years, and redistributes it in ways that fundamentally shape the composition and behavior of ocean floors, volcanic systems, and the chemistry of the rock that eventually finds its way back to the surface in lava flows and eruptions. And this process is happening right now, beneath every continent on Earth, invisibly and silently, driven by the same fundamental forces that built the Himalayas and opened the Atlantic Ocean and are, right now, slowly pulling Africa apart along the East African Rift Valley in a process that, given enough time, will eventually create a new ocean in the middle of the African continent. The Earth is not simply the stage on which the drama of life unfolds. It is a participant, a vast, slow, deep, and restless participant, whose influence on the conditions at the surface is only beginning to be fully appreciated. Chapter 6: The Oldest Rock and the Newest Discoveries. Earth's Deep Time. There is a place in the northern reaches of Quebec in a remote corner of Canada so far from most of civilization that it barely appears on maps most people use, where the ground underfoot contains the oldest known surviving fragments of Earth's original crust. In June 2025, a study published in scientific journals formally confirmed what earlier analyses had suggested. The Nuvvuagittuq outcrop in Quebec dates to approximately 4.16 billion years ago, making it the only known rock formation from the Hadean Aeon, the first and most ancient of the four great chapters into which Earth's geological history is divided. Think about what 4.16 billion years means. The Earth itself is approximately 4.54 billion years old, meaning this rock formed when the planet was less than 400 million years old. This was a world almost entirely unrecognizable from the one we live on now. There were no continents as we understand them. There was almost certainly no oxygen in the atmosphere. The surface was regularly bombarded by asteroid and comet impacts, some of them catastrophic. The Moon, having formed from the debris of a massive collision between proto-Earth and a Mars-sized body called Theia, roughly 4.5 billion years ago, was much closer and much larger in the sky, raising enormous tides that swept across a surface with no dry land to impede them. And yet, in this ferocious environment, rock formed, crust solidified, and some of it, against all reasonable geological expectation, survived, not subducted, not remelted, not eroded away, but sitting quietly in the Canadian wilderness, recording the chemistry of an Earth that existed when only the most primitive microbial life, if any life at all, was present. Scientists who study the Nuvvuagittuq outcrops believe that any fossils or chemical signatures of early life preserved within them could rewrite our understanding of when life first appeared on this planet. This discovery places Earth's deep past in the same conversation as the other remarkable things happening right now. Whether we are looking down at the inner core, sideways through the mantle at buried ancient islands, or at rocks 4 billion years old in Quebec, we are encountering the same fundamental truth. Earth's history is far longer, far stranger, and far less fully understood than we commonly appreciate. In 2024, scientists also discovered a slab of ancient oceanic seafloor, dating to approximately 250 million years ago, just before the emergence of the earliest known dinosaurs, trapped 410 to 660 kilometers beneath the Pacific. This piece of the ancient world, part of the vast superocean called Panthalassa that existed before the Pacific as we know it, had been slowly descending through the mantle for 250 million years, carrying with it mineral records of a world that had long since vanished from the surface. And in separate research, geologists studying the Barberton Greenstone Belt in South Africa found evidence suggesting that plate tectonics, the process by which Earth's surface is divided into moving plates that collide, separate, and slide past each other, may have been operating as long as 3 billion years ago. This matters because plate tectonics is one of the processes thought to be essential for maintaining the conditions that allow complex life to exist on a planet, regulating the climate over geological time, recycling nutrients, and creating the diverse geological environments where life can evolve and flourish. Earth's deep past keeps revealing itself in fragments and whispers. Ancient rocks, buried seafloors, traces of earthquakes 3 billion years old preserved in the crystalline memory of stone. Each discovery extends our timeline backward, showing us a planet with a far, longer, and richer history than any human civilization can truly grasp. And yet, Here is the thought that carries everything together: that same planet is still evolving, still changing, still making discoveries about itself. The inner core is reversing. The magnetic pole is racing across the Arctic. The ocean floor is generating oxygen in the dark. Ancient supercontinent-sized masses sit deep in the mantle, older than 500 million years. And somewhere in the Canadian wilderness, a 4 billion-year-old rock sits in the cold, holding secrets we are only just beginning to read. This is not a planet that has finished its story. It is a planet mid-sentence. Section 7. Dark Oxygen. Life's Rules May Be Rewritten. In July 2024, a paper was published in the journal Nature Geoscience that, if its central claim holds up to further investigation, would represent one of the most significant discoveries in earth science and biology of the past century. The paper, led by Andrew Sweetman of the Scottish Association for Marine Science, described something that had never before been observed: oxygen being produced at the bottom of the ocean in complete darkness by metallic rocks. The conventional understanding of oxygen production on Earth is one of the pillars of biology. Oxygen, the element that most complex life depends on for respiration, is produced by photosynthesis. Plants, algae, and cyanobacteria use the energy of sunlight to split water molecules, releasing oxygen as a byproduct. The oxygen in our atmosphere is the accumulated result of billions of years of photosynthetic activity, starting with the cyanobacteria that first evolved photosynthesis around 2.4 billion years ago, and triggered what is sometimes called the Great Oxidation Event, the transformation of Earth's early, largely oxygen-free atmosphere into the oxygen-rich one that made complex animal life possible. The deep ocean floor, sitting 4 kilometers or more below the surface, receives no sunlight whatsoever. It is absolutely and permanently dark. According to the conventional understanding, it should therefore contain no mechanism for producing oxygen. Life on the deep sea floor should be consuming oxygen, not generating it. The oxygen that does reach the deep ocean floor arrives very slowly, carried downward by the movement of cold, dense water from polar regions that sinks and spreads across the ocean bottom. It is consumed by microbial life and chemical reactions far faster than it arrives. So, when Sweetman's team, working in a vast region of the Pacific Ocean called the Clarion-Clipperton Zone, deployed sealed chambers on the seafloor and measured oxygen levels inside those chambers over time, they expected to see oxygen going down. What they saw instead was oxygen going up. Across 25 separate experiments, oxygen increased inside the chambers, sometimes tripling in concentration above background levels over the course of 2 days. The chambers contained something interesting: polymetallic nodules. These are rock-like formations, roughly the size of potatoes, that form very slowly on certain parts of the deep seafloor over millions of years. They are composed primarily of manganese and iron oxides, along with significant concentrations of cobalt, nickel, copper, and lithium, the same metals used in electric vehicle batteries, which is why they have attracted enormous commercial interest from deep-sea mining companies. The nodules accumulate electrical potential on their surfaces, with voltage differences measured at up to 0.95 volts in some cases. Sweetman's team proposed that the voltage generated by these nodules might be sufficient to split seawater, separating water molecules into hydrogen and oxygen through a process called electrolysis. This is the same basic principle used in industrial water-splitting processes for producing hydrogen fuel. If naturally occurring metallic nodules on the seafloor are generating enough voltage to do this spontaneously, they could be producing oxygen in the complete darkness of the abyss, without any biological involvement and without any sunlight. The implications would be enormous. It would mean that Earth has a source of oxygen that is completely independent of photosynthesis, a geochemical oxygen factory sitting on the deep ocean floor, powered not by sunlight but by the electrochemical potential of metallic minerals. It would transform our understanding of where life might exist and how it might persist. If oxygen can be generated in darkness through electrochemistry, it could potentially sustain life in environments where no photosynthesis is possible, not just on Earth's deep sea floor, but potentially on other worlds. Icy moons like Europa or Enceladus, which have liquid water oceans beneath their ice but receive far too little sunlight for photosynthesis, could potentially have electrochemical oxygen generation occurring on their seafloors. The possibility of life in those oceans becomes, in this light, a little more interesting. It is important to note that the dark oxygen discovery has been controversial. Multiple teams of independent scientists have raised concerns about the methodology of Sweetman's experiments, pointing to potential artifacts in the experimental chambers, and noting that similar experiments conducted by other teams had not shown the same oxygen increases. A 2025 review published in the journal Frontiers in Marine Science raised detailed technical objections. Sweetman and his colleagues have maintained their confidence in the observations and have been working to address the methodological questions. As of early 2026, the first of 3 planned research expeditions was underway to measure both oxygen and hydrogen concentrations around polymetallic nodules. Because if electrolysis is truly occurring, there should be 2 hydrogen atoms produced for every oxygen atom, providing a definitive test. Whether the dark oxygen discovery ultimately stands confirmed or is explained away by some methodological artifact, it has already done something important. It has forced scientists to think more carefully about what processes might be possible on the deep ocean floor, and by extension, on the ocean floors of other worlds. It has opened a conversation about the conditions necessary for life that goes beyond photosynthesis as the only game in town. And it represents exactly the kind of discovery that begins with an instrument apparently malfunctioning and ends, in one way or another, with a fundamentally new understanding of how the world works. Everything connected. Earth as a living system. What is extraordinary about all of these phenomena? The reversing inner core, the migrating magnetic pole, the wobbling rotation, the dark oxygen, the hidden mantle structures, the ancient rocks, is not just that each one is remarkable in its own right. It is that they are all connected, all part of the same vast integrated system, all symptoms of the same fundamental truth, that the Earth is not a passive backdrop for the drama of life. It is an active participant. Consider the chain of connection. The inner core's rotation affects the fluid dynamics of the outer core around it. The outer core's fluid dynamics generate the magnetic field. The magnetic field shields the surface from solar radiation, making complex life possible. The magnetic field's behavior influences the location of magnetic north, which affects navigation systems that human civilization depends on, and the inner core's shape and motion appear to be subtly influencing the length of the day, which means they touch everything from GPS satellites to financial transaction networks. Follow another chain. Ice melts in Greenland, driven by greenhouse gases released by human industry. That meltwater flows to the equator, redistributing mass, slowing the planet's rotation, and wobbling its axis. Those wobbles affect the precision of GPS systems that surgeons use to guide robotic instruments in operating rooms, that pilots use to navigate through clouds, that ships use to move through narrow channels at night. The same process, ice melting, is shifting the geographic pole measurably, by distances that accumulate to tens of meters over decades. And at the bottom of the ocean, where the planet's own electrochemistry may be generating oxygen without any biological input whatsoever, we see a hint that the boundary between life and chemistry is blurrier than we assumed. That the planet itself, through the slow electrochemical transactions of its minerals, may have set the stage for the kind of life that eventually evolved to look up at the sky and ask questions. What all of these discoveries share is a quality that is rare in science: genuine surprise. Not the confirmation of something already suspected, but the overturning of things assumed to be settled. Scientists believed the mantle was well mixed. It is not. They believed oxygen could only come from photosynthesis in the deep ocean. It apparently can come from rocks. They believed the inner core's rotation was at least broadly stable. It is not. They believed magnetic north moved slowly and predictably. It does not. Surprise, in science, is not a sign of failure. It is a sign of progress. Every time the data shows something unexpected, it means our models were incomplete, and that the universe, or the planet, or the ocean is more interesting than we had room to imagine. The great Earth scientists of the past were not wrong. They were working with the tools and the data they had. Now we have better tools: satellites that measure the planet's gravity field from orbit, seismometers sensitive enough to detect earthquakes on the far side of the planet, deep sea landers that can camp on the seafloor at 4,000 meters depth, supercomputers that can model the fluid dynamics of the outer core in 3 dimensions across thousands of years of simulated time. And with those tools, the planet is telling us things about itself that no previous generation ever had the means to hear. There is a philosophical dimension to this that is worth sitting with quietly. We often speak of the natural world as something separate from human history, as context, as background, as setting. We put ourselves at the center of the story and the planet at the periphery. But the discoveries of the past few years suggest something different. They suggest that the planet has its own story, far longer than ours, far deeper, far more complex, and that we are the newcomers, the recent arrivals, briefly making our home on the surface of a world that was old before our ancestors stood upright. The Nuvuagituk rock formation was already ancient when the first eukaryotic cells appeared on Earth. The buried LLSVPs were already sitting at the core mantle boundary when multicellular life was just beginning to experiment with complexity. The magnetic pole was drifting when the first fish learned to breathe air on muddy shorelines. The inner core was already going through its long oscillatory cycle when the first flowers bloomed, when the first birds flew, when the first hominids looked up at the night sky and wondered what was out there. And now, in this particular moment, in this narrow slice of Earth's 4.5 billion year story, we have developed the technology to see down through rock, to measure the wobble of the planet's axis, to detect a reversal in the motion of its innermost layer, to find oxygen being made in total darkness on the seafloor. We are a species in the middle of learning to read the diary of the planet we live on, and it turns out the diary is far thicker, far stranger, and far more beautiful than anyone had guessed. we have come a long way in understanding the Earth. We have mapped its surface in extraordinary detail, drilled into its crust, analyzed its oldest rocks, studied its fossils and its chemistry and its climate. But the deeper we look, the more we realize how much remains. The mantle is still mostly a mystery. The processes driving the inner core's oscillations are still debated. The full nature of dark oxygen and what it means for the history of life is still being established. The future of the magnetic field remains genuinely uncertain. And that uncertainty is not frightening. It is thrilling. It means there are still questions, still discoveries, still moments ahead when a scientist will look at a dataset and realize they are seeing something no human being has ever seen before. The Earth is not finished with its surprises, and we are not finished learning to listen. Oisa, Section 8. The day is getting longer, and the wobble is growing. Here is a fact that sounds like it should matter more than it does. Every day that passes on Earth is, on average, very slightly longer than the day before it. Not noticeably longer. Not in any way you could perceive. The increase, summed up over a century, amounts to roughly 1.33 milliseconds, less than 0.02 of a second per 100 years. But it is measurable, and its cause is revealing. The lengthening of the day is not new. The Moon's gravity has been slowing Earth's rotation for billions of years, through a process called tidal friction. As the Moon pulls on Earth's oceans, it creates tidal bulges that lag slightly behind the Moon's position due to the planet's rotation. This creates a very slight friction that transfers rotational energy from Earth to the Moon, gradually slowing Earth's spin and pushing the Moon into a slightly higher orbit. 4 billion years ago, a day on Earth was only about 6 hours long. A billion years ago, it was around 18 hours. The process is relentless and slow, and it will continue until, billions of years in the future, the Moon and Earth are tidally locked to each other, each showing the same face to the other at all times, assuming the Sun has not swallowed both of them by then. At present, the Moon's tidal friction alone is lengthening our days by about 2.3 milliseconds per century. That is a slow, natural, well-understood process that has been going on forever. But in 2024, a team of scientists using artificial intelligence to analyze 120 years of precision measurements of Earth's rotation found something additional. Since the year 2000, Earth's days have been getting longer at a rate of 1.33 milliseconds per century, attributable specifically to climate change, on top of the Moon's contribution. And this rate was faster than at any point in the preceding 100 years. The mechanism is elegant and counterintuitive. As climate change melts ice sheets and glaciers, enormous amounts of water, which was previously locked in solid form at high latitudes near the poles, are released and flow into the oceans, where they spread out toward the equatorial regions. This redistribution of mass from the poles toward the equator changes the distribution of Earth's mass, and by the same physics that governs a spinning ice skater, it changes the planet's spin rate. An ice skater who pulls her arms in spins faster. An ice skater who extends her arms spins slower. When mass moves from the poles to the equator, Earth effectively extends its arms, and it spins more slowly. The researchers from ETH Zurich and collaborating institutions also found that this climate-driven lengthening of the day was accelerating. Based on current trajectories of ice loss, their models projected that by the end of the 21st century, climate change could be adding as much as 2.6 milliseconds per century to the length of the day, making it the dominant influence on Earth's rotation speed, surpassing even the Moon's tidal friction. The same redistribution of mass is also doing something to the orientation of Earth's rotational axis. The second study by the same research team found that the melting of ice and the movement of groundwater were causing the pole of Earth's rotation, the geographic North Pole, to drift at an accelerating rate. The geographic North Pole, like magnetic north, is not absolutely fixed. It wanders slowly over time due to various geological and hydrological processes. But the team found that roughly 90% of the periodic fluctuations in the axis position over the 20th century could be explained by changes in groundwater, ice sheets, glaciers, and sea level, with only the remaining 10% attributable to Earth's interior dynamics. As ice melts and groundwater is pumped from underground aquifers and flows toward the ocean, the balance of mass around the planet shifts, and the rotational axis shifts with it. The geographic North Pole, not just magnetic north, but the actual axis of Earth's spin, is moving, nudged by human activity at a scale that satellites and ground-based observatories can now measure precisely. None of this constitutes an emergency. An extra millisecond or two per century in day length will not be noticed by anyone living today, or by anyone who lives for many generations to come. The wobble of the pole is similarly tiny on human scales. But the fact that these changes are measurable, that they have fingerprints connecting them specifically to processes driven by climate change, and that they are projected to accelerate. These are meaningful signals about the degree to which human activity is now operating at a planetary scale, influencing not just the surface of the Earth, but its rotation, its balance, and the very rhythm of its days. The Earth, it turns out, does not simply provide a stage on which we play out our history. It responds to us. It records what we do in its ice and its rock and its spin rate, in its axis of rotation and in the length of its days. And, if you read it correctly, it tells the story of our time with a precision that no historian could match. Section 9. The Grand Picture. A Living, Breathing World. We have traveled a long way tonight. We have gone from the absolute center of the Earth, where a solid iron sphere is slowly changing its relative rotation and deforming its shape under pressures that make our entire atmosphere seem like a whisper. We have moved outward through the liquid outer core, where the churning of molten metal generates the magnetic field that shields our world, and where changes we are only beginning to understand are causing that field to wander, accelerate, slow, and develop regions of unusual weakness. We have passed through the deep mantle, where ancient buried structures the size of continents have been sitting undisturbed for 500 million years, anchoring the planet's geological behavior and feeding mantle plumes that surface as volcanoes in Hawaii and Iceland. We have found that even the continents themselves are being peeled apart from below by mantle waves that carry fragments of ancient crust into the depths of the ocean floor. And we have reached the surface and looked out at the deep ocean floor, where metallic rocks may, the question remains genuinely open, be generating oxygen in complete darkness through chemistry alone. And through all of this we have found Earth to be something quite different from the static, sleeping, solid sphere that common intuition suggests it is. Earth is a machine. It is an enormous, ancient, multi-layered machine running on the heat left over from its formation billions of years ago, supplemented by the continuing heat generated by the decay of radioactive elements throughout its interior. every layer interacts with every other layer. The inner core influences the outer core, influences the magnetic field, influences the upper atmosphere, influences the surface climate, influences the ice sheets, influences the rotation rate, influences the distribution of stress on tectonic plates. These are not separate systems. They are one system, and the lesson that Earth science is learning more clearly every year is that changes in any one part of this system ripple through all the others, often in ways that are subtle and slow, but nonetheless real. The unusual things happening to Earth right now are not signs of doom. They are not harbingers of catastrophe. The inner core's rotation reversal follows what appears to be a natural 70-year cycle that has happened before and will happen again. The South Atlantic anomaly is growing, but similar weak spots have appeared and disappeared in the magnetic field throughout Earth's history, without triggering catastrophe. The buried supercontinents at the base of the mantle have been there for at least 500 million years, and will almost certainly be there for hundreds of millions more. The day lengthening is so slight as to be imperceptible to human experience. The dark oxygen, if real, represents life's creativity rather than any threat to it. What these phenomena are, taken together, is a reminder that we live on a dynamic planet, a reminder that the systems that maintain the conditions for life on Earth, the magnetic shield, the tectonic cycling of materials, the chemical balance of the atmosphere and ocean, are not static gifts that will persist unchanged forever. They are active processes, running continuously, maintained by the ongoing motion of the Earth's interior and the interactions between its many layers. They are the product of a very specific and fortunate set of conditions that have existed on this planet for billions of years, and that continue to make this small, wet, spinning rock one of the most extraordinarily complex and improbable places in the known universe. When you lie down at night on this planet and feel its solidity beneath you, you are resting on something that is anything but still. Beneath you, right now, liquid iron is churning in a sphere thousands of kilometers wide, generating the magnetic field that will protect you from the sun's radiation tomorrow. Beneath you, mantle plumes are rising slowly from ancient reservoirs that have been there since before animals existed. Beneath you, tectonic plates are grinding against each other in silences so profound they are measured in millimeters per year, building pressure that will one day release in earthquakes and eruptions. Beneath you, the solid inner core is slowly tracing its backtracked path, responding to forces that connect it to everything above it all the way to the sky. And in the deep ocean, just possibly, rocks are making oxygen in the dark. The world is stranger and richer and more alive than it appears. The ground beneath your feet is not what you thought it was. It is a story, billions of years long, still being told, still being written, still full of chapters that no one has yet discovered. And that, somehow, is one of the most peaceful thoughts in the world, that there is still so much to know, that the universe, even the one that extends downward from where you sleep, is still generous with its mysteries, that we live in a time when new chapters of this story are being written and read, when instruments we built and launched into space are measuring changes in the heart of the planet, when seismologists are sitting in universities from Utrecht to Los Angeles to Beijing, poring over earthquake waveforms and saying, with the quiet excitement of genuine discovery, something is changing, something is moving, something here is really unusual. You can rest in that knowledge. It asks nothing of you. It is simply there, beneath you, going on as it has always gone on, the great and patient machinery of a living planet doing what it has always done, in its own time, on its own scale, for its own deep reasons. Closing. Drift into sleep. And so we arrive, as we always do, at the threshold. The threshold between knowing and not knowing, between wakefulness and sleep, between the busy surface of things and the deep, quiet regions underneath. The earth beneath you is moving tonight, just barely, just quietly, just as it always has been and always will be. The magnetic field that wraps your body right now, in this moment, on this night, as you lie still. That field is real and present and humming with the motion of liquid metal far below. The compass inside your phone knows something about where north is, and north has wandered a tiny bit closer to Siberia today than it was when your grandparents were born. These things are true, and they are interesting, and you do not have to do anything about them. You can simply know them. You can simply carry them with you, lightly, into sleep. Let your breathing slow now. Let your thoughts settle the way sediment settles at the bottom of a still lake, slowly, gently, without effort, finding their own level. The day is done. The questions are interesting, but they are not urgent. They will be there tomorrow, and the scientists will keep working on them, quietly and carefully, and with great curiosity. And someday there will be more answers and more questions after those. That is the nature of this work. That is the nature of this world. If this video helped you find a little peace tonight, if it gave your mind something beautiful to rest on, please, before you drift away completely, hit the like button or leave a comment to let me know you were here. And if you want more nights like this, more deep dives into the extraordinary ordinary, more science delivered slow and soft and in the dark, then subscribe to The Science Pillow. New scripts appear when they're ready, never rushed, always for you. Sleep well. The earth is keeping watch. It always has been.